The early development of RDF led to important contributions towards defense against anticipated and actual enemy air attack, the air offensive against the enemy, an incessant struggle for the mastery of the sea, and the great group of operations which culminated in the D-Day landing. The darkening skies of the mid-1930s, with Germany openly rearming, led to great concern as to the state of our air defenses against superior, possibly overwhelming German air forces. To advise the Chief of Staff's committee on what measures should be taken, the Tizard Committee of prominent scientists had been set up. At that time, only visual methods of detecting enemy aircraft were known, in addition to some acoustic devices involving large concrete reflectors with a maximum range of about 20 miles and considerably shorter ranges in usual practice. The committee, therefore, examined proposals to utilize reflections from aircraft based on ionosphere research work at Slough, leading eventually to an experimental demonstration at Daventry on the high-power CW transmitter in conjunction with modified ionosphere reception equipment. The results were sufficiently convincing to set in motion immediate and secret experiments on more elaborate lines at a station chosen for its remoteness on the east coast. Here at Orford, in May 1935, a small team of experimental scientists was detached from Slough to conduct these first experiments in RDF. By the end of the year, the original ionospheric gear working on 50 meters, now converted to the shorter wavelength of 26 meters to avoid Z-layer effects, was achieving ranges on typical aircraft at 10,000 feet up to 45 miles. During the early part of 1936, parallel experiments were started on the shorter wavelength of 13 meters, the choice for mobile requirements of a wavelength half that of 26, conferring a sufficient reduction in size and height of aerials to make gear based on this wavelength a practical proposition on portable masts. By early 1937, the mobile equipment now transferred to Bordsey, where the major 26-meter experiments had preceded it a year previously, had solved the problems of range, sense, DF, and height. And in March of that year, the first radar three-dimensional fix was achieved. During the summer, the experiments were transferred to Dunkirk for field trials. Radiated illumination from the transmitter was all round. The receiver equipment being one-man operated, giving by the throw of a switch, search, range, DF, and height successively. Phasing of the receiver aerials could be carried out at the receiver itself. The equipment, conveyable in lorries or trailers, was the precursor of the mobile equipment which later operated in the Middle East to supplement the high-power fixed stations of CO type, chain overseas, developed on CH principles. CH, chain home, was the name by which the major experiments at Bordsey on 26 meters had become known. By 1937-38, 4 out of 5 of the estuary stations sited at Bordsey, Brumley, Canewdon, Dunkirk, and Dover were in operation, working at a mast height of 240 feet and by then giving DF fixes height and sense. At the Munich crisis of September 1938, 3 additional stations constructed with mobile type equipment were erected in 10 days on the east coast to extend some cover to the estuaries of the Forth, Humber and Wash. The jolt received at Munich gave rise also to energetic action in which by May 1939 14 further stations, additional to the original 5 estuary stations, were erected along the east coast on 240-foot wooden receiver and transmitter towers. By this means, substantially continuous cover was given along the east coast, and the stations were put into immediate operation to guard against an undeclared attack from Germany. To make this possible, some of the technical staff from Bordsey Research Station concerned themselves wholly with the installation problems involved, working in conjunction with staff from No. 2 Installation Unit Kidbrooke, and in the maintenance of these stations on the air, continuing right through the declaration of war until relieved by the formation of 60 Group in February 1940. After the outbreak of war, a further chain of stations was erected along the west coast, mainly during 1940. The incidents of war coincided with the realization that the CH stations, owing to long wavelength sighting difficulties, were unable to cope with the early detection of low-flying aircraft. To meet this menace, the so-called CD, coastal defense type of station, developed at Bordsey during the previous 18 months, using for the first time rotating aerials, was adapted in a few weeks to produce some 5 CDU, coast defence U-boat stations, to guard Scapa Flow at the extreme north of Scotland, the Orkneys and Shetlands. Subsequently, CD was modified to equip CHL stations, chain home low flying, with which both coasts of the British Isles were within the next year equipped to a large extent. These stations gave good low-flying cover using split beam technique with its greater accuracy in azimuth. At an early stage at Bordsey, the necessity for the development of some equipment whereby friendly and hostile aircraft could be distinguished was apparent. In the IFF identification friend or foe system, the transmitted pulse was received by the IFF equipment carried in friendly aircraft, which re-radiated an amplified and coded signal which could be distinguished by the ground station receivers. Some important experiments by the airborne group were being carried out on the precursors of 1.5 meter AI, aircraft interception, and ASV, air-to-surface vessel, in parallel with the CD, IFF, and other experiments at Bordsey during the brisk 18 months prior to the outbreak of war. In early flying with experimental type gear, rough CRT picture maps of coastlines were an incidental outcome. Experimentation from 1935 onwards had provided real early warning insurance against attack. The necessity of maintaining exhausting standing patrols of the incomparable but few Hurricanes and Spitfires and the men that flew them was obviated by RDF's 20 minutes warning, and the Battle of Britain was won. But although the day battle in the air was won, RDF had an ever-increasing part to play in the air war. Bawdsey Research Station, transferred at the outbreak of war to a temporary home in Dundee, and later as TRE to more permanent quarters at Swanage, now devoted a great part of its research program to problems created by the new phase, the night battle. The defensive problem had changed. Instead of guiding fighter squadrons to large forces of hostile bombers by day, it was now necessary to guide a single fighter to a single enemy aircraft by night. During the summer and autumn of 1940, AI Mark III, using horizontal polarization, was operational in Blenheims. It was not free from ambiguity and possessed poor DF facilities. And in the Mark IV equipment fitted to bow fighters, vertical polarization was introduced. AI Mark IV, still on 1.5 meters, gave ranges from 20,000 feet down to 600 feet, and was the main AI equipment in use until autumn 1941. Meanwhile, owing to the limited range of AI, a form of ground control was essential to guide the night fighter close enough to the hostile bomber for AI contact to be made. The 2 or 3 minutes delay involved in passing information to the filter room could be eliminated by controlling the fighter direct from the ground RDF station. It was realized that accurate fighter direction demanded a new form of display which would present both range and bearing information in such a way as to give the ground RDF operator the target's planned position immediately and without calculation. Research on this problem produced in early 1940 the first successful PPI tube. Meanwhile, research was being carried out on the problems of a suitable rotating aerial system and of more accurate height estimation. In August 1940, the combination of PPI and 1.5 meter ground RDF, with the aerial rotating in step with the PPI trace, was given successful trials at Worth Matravers, to be followed shortly by the construction at Darrington of the first mobile equipment for the ground control of interception, or GCI. This station became operational immediately, but test flights showed that at certain vital ranges the aircraft was lost. To overcome this, a gap-filling technique was devised, which depended on phasing of the 2 halves of the transmitting aerial system. A similar technique led to improved accuracy in height finding, and the success of GCI was now sufficiently assured for 6 stations to be erected by the beginning of 1941. This new control system resulted in a steady rise in enemy loss figures during the months that followed. Later, fixed GCIs on 1.5 meters were built, incorporating many improvements such as the Skyatron, and finally it was possible for 3 controllers to work from the same station or happydrome, each handling a separate interception, for which, as in many other ground equipments, the heavy engineering requirements were covered by RAE. It was known that the enemy was preparing to jam on 1.5 meters, and to anticipate this move, a GCI equipment was developed on 50 centimeters, this being close to one of the wavelengths on which the enemy's own radar was operating, and one therefore unlikely to be jammed. The first of these 50 centimeter GCIs, known as AMES Type 11, was operational in March 1942. When the enemy used his 1.5 meter jammers, the first occasion being the Scharnhorst and Gneisenau Channel episode, stations in the Dover area were seriously affected. The advantages which would follow on the use of shorter wavelengths had been recognized since the first days of RDF. But the limitations of the earlier RDF equipments on wavelengths of 1.5 meters or more had to be faced during the early years of the war, since no practical technique for much shorter wavelengths was then available. These limitations on 1.5 meters presented increasing drawbacks as the war progressed. Drawbacks mainly due to the floodlighting inevitable on these wavelengths with aerial systems of reasonable size. Thus, 1.5 meter AI Mark IV experienced ground returns which filled the CRT and severely curtailed the maximum range, making it impossible to detect a target at a range greater than the AI aircraft's height above ground. So, AI Mark IV could not be used at all at very low altitudes. Moreover, the DF was comparatively poor. In the same way, height finding with CH, CHL and GCI was inaccurate and susceptible to sight, and these systems were very easy to jam. These drawbacks could be overcome if the radiation could be concentrated into a very narrow beam. The fairly new types of valves, the cavity magnetron and the klystron, became available by the summer of 1940, providing opportune solution to the problems of adequate radio frequency power radiation and the provision of local oscillators on wavelengths in the 10 centimeter or S-band region. Work could now go ahead on centimeter wavelengths to provide the narrow beam required. At the same time, the design of compact aerial systems was facilitated. The first application was AI, since at this time the danger of night raids was greater than ever, and AI needed the advantages associated with narrow beams. Two methods of scanning with the beam were evolved during the later part of 1940. The first was the spiral scan, with which was developed a new type of display showing range, bearing and elevation simultaneously. Test flights with this equipment were made in February 1941. When further developed, the equipment became known as AI Mark VII, of which 100 were produced and fitted in Beaufighters, the first AI Mark VII squadron being operational in March 1942. AI Mark VIII, a higher power version of Mark VII, became a standard fitting in Beaufighter and Mosquito night fighters from January 1943 onwards. Mark VIII gave a greater maximum range than Mark VII, some 5 miles on a medium bomber, and incorporated facilities for IFF interrogation, homing beacons and beam approach, BABs. The fundamentally new techniques associated with centimeter radar equipment necessitated changes in operational methods. To assist in a rapid and smooth changeover, PDS, Post-Design Services, formed in the spring of 1942, helped with their specialized knowledge to train service personnel on squadrons in the operational and maintenance problems involved, and proved an essential link in the introduction of new airborne equipment into the service. Another type of scan was helical, working with 2 tubes, one giving range azimuth, the other elevation azimuth display. Further developed by the Americans, the equipment became known as SCR 720. Its readoption by this country belongs to a later phase of the war, that of the Allied air offensive. The introduction of centimeter equipment into aircraft raised the problem of the use of ground beacons working on meter wavelengths. A solution was provided by the introduction of the Lucero interrogator, which, used in association with centimeter sets, triggered off 1.5 meter ground beacons or responders and enabled the centimetre aircraft installation to receive and display the responder pulses. Successful air defence would not have availed had the sea routes for food and essential imports proved impossible to defend. Early Bawdsey experiments on airborne 1.5 metre RDF had shown that returns could be obtained from ships, and shortly after the outbreak of war, ASV Mark I was fitted to Coastal Command Hudson's and Sunderland's. Homing beacons were set up, and the ASV equipment was used for homing on return from patrols, range limitations restricting the equipment's use on hostile ships and submarines. Better aerial design, giving improved ranges, led subsequently to the development of long-range ASV, ASV Mark II, the equipment becoming operational by July 1941. Used until early 1942, mainly for locating convoys during escort duty, ASV Mark II, with gradual improvement in ranges, registered increasing successes in night attacks on shipping. Some success was also achieved against submarines in the Bay of Biscay with the aid of moonlight or flares. The introduction of the lee light further extended the scope of the equipment, enabling ASV Wellingtons to operate at night with success against surfacing U-boats and to win the first Battle of the Bay in June 1942. As early as 1939, the desirability had been foreseen of a radar navigational aid in locating targets when we should pass to an air offensive over the continent. Experiments were conducted on a path difference system G, a possibility originally suggested in 1938 as a solution to the blind approach problem, and the first eastern chain, Stenigot, Daventry and Ventnor, was ready to operate in July 1941, in conjunction with 24 handmade airborne sets fitted to 115 Squadron. By February 1942, several hundred aircraft had been equipped, and a month was spent in practicing on the back radiation of the chain over image positions of German targets. The first G raid was on Essen, carried out by over 200 aircraft on March the 8th, 1942. The success of the raid led to the equipment with G Mark I of all aircraft under Bomber Command. By the spring of 1943, enemy jamming had begun to interfere with its use over Germany and Holland. G Mark II, with frequency flexibility, was, however, now in service, and on special occasions, such as the Myrna Dam raid, the chain stations came up on an additional frequency as the bombers were approaching their target. The introduction of G made possible new standards of accuracy in navigation. An important development of technique which depended on G was the concentration in time and space of our attacking bombers, which enabled the enemy's defense to be saturated. Although the accuracy of G fixes in general far exceeded Bomber Command specifications, which allowed for a 15-mile error, it fell short of the requirements of a device suited for blind bombing. In May 1941, systematic work had started on a blind bombing system, OBO. The principle employed was ground control of the bomber by range measurements from 2 ground stations. Both stations transmitted pulses on the same radio frequency, but on different pulse recurrence frequencies, the bomber carrying a pulse repeater to ensure adequate signal strength. One station, the CAT, guided the bomber onto and round a constant range track passing directly over the target. The other, the mouse, signaled the appropriate moment for bomb release. 6 oboe-equipped aircraft took part for the first time in the operation on the 20th of December 1942 against Krupp's Works Essen. A limitation of the Mark I system was that each station could only handle one aircraft at a time, the average period required from taking control to signaling bomb release being 10 minutes. The limitation was counteracted by the Pathfinder technique associated with the development of target indicator bombs, which enabled a few Pathfinders to illuminate the target for a large number of heavy bombers, a technique first used on the 5th of March 1943. This opened the Battle of the Ruhr, when target indicators were dropped by the Pathfinder force on Essen, with 400 heavy bombers following up. So began bombing in 10/10ths cloud, a possibility utterly unforeseen by the German High Command. The assumption that 1.5 meter oboe would be rendered operationally useless by jamming before a later type could be brought into service led to the provision of an alternative blind bombing method, the H system. The H system depended on the measurement of range from 2 ground stations which were triggered off by transmissions from the aircraft. The fixes, as in oboe, were thus given by the intersection of circles, and not as in G by the intersection of hyperbole, and the standard of accuracy required for blind bombing could be attained. The system was suggested in 1940 as an alternative to G, but was not at that time adopted owing to the limited number of aircraft directable at one time and the possibility of the enemy homing onto our own aircraft's transmissions. In June 1942, the call for an alternative to oboe led to intensive work on the H system. By modifying the existing G equipment, GH was produced. GH, used for mine-laying operations, came into full operational use on D-Day. The limitation in range of oboe, GH, and G, imposed by their dependence on ground stations, restricted the navigational and blind bombing cover of long-range bombers to Western Germany, from which war industries were already withdrawing. Whilst from considerations of fuel supply, the bombers were capable of far greater cover. The operational value of a self-contained equipment independent of ground stations and dependent only on the radar recognition of local topography had been long foreseen by radar scientists. Serious work on this problem had been shelved until the rapid development of centimeter technique in 1941. Tests were now carried out using the helical AI scan in a Blenheim with a beam tilted downwards, and responses of isolated targets were discernible on the range azimuth display. This immediate success initiated the program of research and development which resulted in H2S, the bulk of this program being carried out at TRE's new home at Malvern. The beam, broad in elevation and narrow in azimuth, rotated at 60 revolutions a minute in step with the trace on the normal PPI display, and gave a picture in which land showed up against water and towns or isolated structures against countryside. H2S was in operation by the end of 1942, and by October 1943, 1/6 of Bomber Command's total sorties carried H2S, operating at the limit of their flying ranges. The development of 3 centimeter X-band technique later made possible PPI pictures of greater definition essential to the bombing of Berlin. Meanwhile, the development of oboe on centimeter wavelengths had continued for use on special targets where the highest precision bombing was required, and in the spring of 1944, a mobile centimeter equipment, Mark IIM, was brought into service. It was not only for navigational accuracy that our bombers relied on radar, but also for protection against enemy interference. Bomber defense at first envisaged the protection of the individual bomber by means of various warning devices: boozer, fish pond, monitor, and the most successful, AGLT. But the technique of concentrating our attacks into a tightly packed bomber lane brought into prominence methods suited for protecting the lane as a whole. These methods were of two kinds: jamming or deception of the enemy radar by means of countermeasures, and shooting down his fighters on their way to attack by our own protective fighter sweeps. The first countermeasure equipment to become operational was mandrel, an airborne jamming transmitter radiating a band of noise extending over 10 megacycles and used against the enemy's Fryer and early warning system. A limited number of bombers in each sortie carried mandrel to reduce the coverage of the enemy's long-range equipment. The second equipment, moonshine, was a pulse repeater equipment, which enlarged and lengthened echoes obtained on the Fryer system, thus simulating a large formation of aircraft. Moonshine, first used operationally in July 1942, was immediately successful. 3 fighters so fitted, causing the entire enemy fighter force in the Cherbourg area to become airborne. In 1941, a device later known as Window had been suggested to counter the enemy Würzburg 53 centimeter radar system. This device relied on the release by aircraft of strips of metallized paper foil which produced resonant reflections highly confusing to the enemy's ground radar traces. Its operational employment was postponed as it was foreseen that once used it would soon be imitated. But development continued, and in July 1943, Window was successfully employed in a heavy raid on Hamburg. Thereafter, Window became a normal accompaniment of every major raid. During the winter of 1944, a third of Bomber Command aircraft were equipped with Carpet 2, a barrage jammer which explored a frequency band of about 40 megacycles until reception of a signal, to which it locked automatically and then radiated for a predetermined time 1 watt of noise spreading over a bandwidth of 1 megacycle about the signal frequency. Serrate, a directional listening apparatus which considerably increased the range of initial AI contacts, was carried by fighters to enable them to home onto the AI transmissions of enemy fighters. It was used in conjunction with normal AI in defense of our bomber sorties, and was first put into operation by Fighter Command in the autumn of 1943. It had been anticipated that AI Mark 8 would be difficult to operate in high concentrations of window. The helical scan American SCR 720 was therefore modified to RAF requirements and adopted as AI Mark 10, replacing all AI Mark 8 sets. In addition, the greater volume of space explored by AI Mark 10 was found of value to freelance fighters defending the bomber lane. In November 1943, Mosquitoes, the first aircraft equipped under this program, went into action. As the American and Canadian armies gathered in Britain for the assault on Europe, the quantity of transatlantic shipping to be protected from U-boat attack constantly increased. The limitation on ASV Mark II and LRASV in anti-U-boat operations, now imposed by the enemy's 1.5-meter listening activities, made a reduction in wavelength essential if radar was to continue its part in the destruction of the U-boat menace, whether in mid-Atlantic or in the Bay. The adoption of a shorter wavelength could conceivably also increase the ranges obtainable on U-boats. There was in H2S an existing equipment which, with some modifications, would meet most of the requirements of Coastal Command. The H2S equipment was therefore adopted for development into ASV Mark III, the modifications including alteration of the scanner for low flying over the sea. ASV Mark III, first fitted in March 1943 to Lee Light Wellingtons, was supplemented by its American counterparts Marks IV and V. These centimeter ASVs scored considerable successes in June against U-boats and won the Second Battle of the Bay. Later, an improved version of ASV Mark III was developed, known as Mark VI. This was a higher power set, and the Mark VIa version was fitted with automatic following facilities in azimuth and means for coupling the movements of the radar beam with the Lee light. Work had started in 1942 on X-band, 3 centimeters, a primary application being ASVX for the Fleet Air Arm, for whose aircraft the smaller equipment was particularly appropriate. ASVX, later known as ASV Mark 11, became operational in Swordfish towards the end of 1943, and in Barracudas in mid-1944. The equipment's greatest use was as a navigational aid, the PPI display being invaluable to the aircrew. ASV Mark 11 was used in escorting Russian convoys in the Arctic in April 1944, and in successful combined operations with Coastal Command. By winning the day battle of Britain in 1940, survival to fight and win the night battles of the Blitz in 1940-41 had been secured. This further victory making possible the Allied air offensive in 1942-43. But this offensive, though it accomplished havoc among the enemy's war industries, was not an end in itself, but a means to the invasion of Europe on June the 6th, 1944. For over 2 years previously, all radar research effort in the laboratories had been devoted towards this end. And when the time came, perhaps no single weapon was found to have a wider variety of uses than radar. Type 16 fighter direction stations on 50 centimeters had previously controlled our sweeps over France and enabled them to force back enemy aerodromes from the coast. In the English Channel, from March to August 1944, Swordfish equipped with ASVX hunted down E-boats, R-boats and midget submarines. On detection, flares were dropped, and bow fighters, judging their ranges with AI Mark 8, attacked the illuminated targets with rockets. Enemy radar installations were either destroyed, jammed, or deceived by counterfeit presentations. For their destruction, exact plotting on the map was necessary, aided by ping-pong, a listening-in device. Jamming was accomplished by shipborne mandrel and carpet, and by airborne mandrel, and the VHF jammer, airborne cigar. The contrivance of radar signals misleading to the enemy involved at least one completely novel maneuver. This was the dropping of window by orbiting planes to simulate shipping approaching Fécamp and Boulogne. G and GH guided the planes taking part in these operations. Spoof signals on the enemy's CRT were reinforced by shipborne moonshine and ship-towed balloons. At the last moment, enemy gun positions were bombed and rocketed by aircraft using oboe. Window and mandrel were used in screening the transport of airborne troops carried by aircraft using G. As a supplementary navigational aid, Eureka beacons were set up in England and on ships in the Channel. Supplies and reinforcements were guided to the right spot by aircraft using Rebecca Eureka. This interrogator and beacon system, originally evolved in 1941 and adopted for the dropping of supplies to partisans in occupied Europe, had been employed also in the Sicilian and Salerno landings. The ships sweeping channels through the minefields were guided by G, and 2,000 vessels were fitted with G to ensure the accurate navigation of these channels. Early warning and GCI Type 21 ground stations were transported on D-Day together with some Type 11 and Type 15 installations for immediate follow-up on the continent. With the continental base secured, further grim fighting led the Allied armies to the Seine, the Mars, the Rhine, and Germany, crowning the long years of hard endeavor with complete victory.